As you can see, I have a molecular dynamics simulation of this gas A and gas B. Gas A is red and gas B is blue. Well, without ever doing the simulation, you know what will happen. Intuitively, these two gases will mix. So probably you will see something like this. The red and the blue molecules will, or the balls will mix. Will mix. That's the thing that you actually observe physically. So more or less, you have an idea of what is thermodynamics, specifically the second law. Further, take a look at this. The law of thermodynamics will state the spontaneity, specifically the direction where the process will go. As you can see, the logical choices from 1 to 2, wherein the blue and red balls will mix here. You don't observe something in nature that this final state wherein these two colors are mixed will separate spontaneously and come back here at state 1 wherein the balls are separated in color. Never. Okay, how about this? Well, assuming I want to go to Starbucks and I want to drink my favorite coffee. Assuming I put my coffee in the table, more or less you will know what happens. The heat will go out. Okay, that's the natural thing that will happen. We don't observe something like this one, wherein the heat will go in the coffee. Eventually, the coffee will get hotter. And that will never happen in nature. So more or less, we all agree that this this is a natural phenomenon where heat is escaping from your coffee. After several minutes, you'll feel that your coffee is cold, and you want to heat it again so that you will enjoy your coffee. So again, the second law of thermodynamics dictates the direction where the physical phenomena will happen. Let's see, for example, this coffee. The heat will go out and never the other way around. So that's how important the second law of thermodynamics is. Again, the backward process never happens. Okay, you'll never see this. So let's address spontaneity by introducing the second law of thermodynamics. In short, let me try to narrow it down because the time is not that we don't have the luxury of time. It's quite my presentation is short, so let me give the definition. It is a law to govern the direction of a process. Okay, specifically the direction. Why do we need to know the direction when we know that it's quite obvious? Okay. As you can see, these red and blue balls, that's quite obvious. They will mixer. Why do we need that? Do you really need a law for this, for enjoying your coffee? You will know that somehow that's already as well established that the heat will just evolve out of this coffee cup. Okay. How about for something that is not that obvious? Say for example, we have a mixture of these two gases or something like this. This will this particle from this initial condition be something like this in the final condition, wherein these two gases will react and will form one gas. Okay, so you can see that's not pretty obvious. So normal question is, how do we address spontaneity if we do not have any prior experience to the said system? Well, we should introduce this thermodynamics, specifically the second law. Let me give a classical definition for the second law of thermodynamics, wherein we know that this never happens from the closest statement that heat will evolve from a cold body towards the hot body. We never experience that, so that's a big cross. That's a big X. This is also a big no from Kelvin Planck statement, wherein you see that as heat is evolved from the heat reservoir to the engine, it simultaneously does work. That's also not allowed. Okay. Those are the classical definitions, but here we have a definition here. I have specifically chosen this kind of form because I believe this is quite very useful for engineers. As I have said, I have graduated from engineering. There are different forms for sciences, specifically chemistry and physics. But the one that is very useful for engineers, I think, is this one, which is a simple relation about the ratio about the heat and the temperature should be less than or equal to 0, meaning it should be negative. Okay. We have this refrigerator, of course. Normal parts of the refrigerator, you have the evaporator and the condenser, wherein heat in, there's a heat out. If you try to get the sum of that from the heat in over the temperature of the input temperature, and this one is the output temperature. If you subtract the two, simply because the heat out is negative, or it's going out from the system, the convection for the heat in is positive because it's going in the refrigerator, should be less than or equal to 0. So that's the condition. Okay. Well, if you try to understand the second law of thermodynamics, it could be expressed in something like this. The entropy is equivalent to the disorder, as you can see from the molecular dynamics simulation here, plus, of course, it could be modified by heat transfer effect. As you can see, heat could influence the entropy of the system, because as you know that the entropy is about disorder, so introducing heat could increase this entropy. Okay, so the difference in entropy is the entropy production. Okay, and of course you have an integral here. We sum it from process, or from the start of the process to the final stage of the process. This ratio of heat with respect to temperature. Okay, this is very important. If we add the system and the surroundings, that is called the entropy of the universe, it should be greater than or equal to 0, meaning it's positive. Okay, so let's try to see what am I talking about. Okay, as you can see, we have this coffee. The surrounding is at 25 and the coffee is 45 centigrade. If we assume initially, we make this foolish guess that the heat will go from the surroundings to the coffee, so the system will further gain 10 joules of heat. We divide it by the temperature. So for the other side, for the surrounding, the heat there is negative. We should divide it by the temperature of the surrounding. Of course, we utilize the absolute temperature, so that's 25 plus 273 to convert it to kelvins. And if we do the calculations in our calculator, we'll find out that that's negative 0.0021 joule per Kelvin. So what can you see? The entropy is negative. So if the entropy is negative, we violate this rule, which is very obvious because the entropy should increase. The entropy of the universe should increase, should be positive. Here, we violated the coffee, our coffee, because we know that heat can never go from the cold surrounding at 25 centigrade to the hot coffee, which is 45 centigrade. It should be the other way around. Therefore, if we assume that Q is negative, such as in the next slide, then of course the sign will be reversed. So instead of negative, you'll get positive, and the entropy is greater than zero. It's spontaneous. This is the thing that we observe physically, that the coffee eventually gets cold because the heat is transferred from the hotter body to the colder body. Okay. So more or less we get the idea of what is the second law of thermodynamics is. It may seem vague at the moment, but if we try some examples, like for this design examples, we can see that this entropy thing is a very important property to be considered in designs. Okay, it's equally important with the first law of thermodynamics, as we should see in the next slides. Okay, now let's get back to the idea here. We have two gases, that's the yellow gas and the blue gas. Initially they're the reactants, but how do we know in the final product that these two reactants will react and have a final form, such as they combine to produce one gas or one entity? Well, we know from thermodynamics 1 that heat could be expressed in terms of enthalpy. So the surroundings will have the same enthalpy, but it's negative in value. So to get the entropy of that, we just need to divide it by the T, or the for the absolute temperature of the surrounding. If we use the previous argument that we have, that the system and the surroundings, which is the universe, should have this kind of form. Okay, we have delta S of the system minus delta H over T. This delta S of the system minus delta H over T should be greater than or equal to 0, because we have shown that for the coffee. Okay, now from basic algebra, we just simply multiply the whole thing by negative T, then we get this expression, that the enthalpy minus the product of the temperature and the change in entropy must be less than or equal to 0. Less than for irreversible processes and equal for reversible process. We will see the power of this equation later when we consider the design problem. But for now, you just have to bear in mind that there are two things to be considered here: energy in the form of enthalpy, and disorder in the form of entropy. Okay, so that's it. That's a very powerful equation to address spontaneity. Okay, now is this invention here that I am presenting spontaneous? Okay, will the process that will occur in this invention occur in a manner that is spontaneous? I mean, we have an input of air here. We assume that it could be modeled as an ideal gas with a specific heat of 1. Okay. These are the conditions. They are 21 centigrade and 5 bars. Now, if it exits here at point 2 and 3, they produce something like hot air and a cold air. So you might get the idea that maybe it won't work, because without the input of heat, how can you get something like a hotter outlet? Without the input of work, how do you expect to have a cold outlet? It's entirely void of work and heat. meaning this device is successful in producing two outlets with a hot and cold outlet without ever having something like a heater or such kind of okay. So is will it be possible to construct something like this one or design something like this one? Well, you can test it. You can have a CAD model of this, then you subject this to a finite element analysis, computational fluid dynamics, wherein you will simulate airflow here, and then hopefully you will get the conditions here at the outlet. But if you don't have those kind of sophisticated equipment at home, or you say you don't have yet the license, or you cannot have, you must make some initial calculations. Well, we turn to our classical thermodynamics, second law of thermodynamics, to determine if this works. Okay, so let's try. Well, at the start, it's wise for you to test if it is balanced with respect to mass and energy. Okay, so the first one, we have m1 equals m2 plus m3. That makes sense because m1 is the input and the output should be m2 and m3. So this one makes sense. The next equation, we assume that the potential and the kinetic energies are negligible. Okay, so what's left from our thermodynamics one is plainly enthalpies. Okay, so here we have the input m1h1 and we have two outputs m2h2 m3h3. So let's try to test the invention. M1 could be replaced by M2 plus M3, so you have this minus M2H2 minus M3H3. With a little bit of algebra, you'll find that this is true. M2 multiplied by quantity H1 minus H2 plus M3 quantity H1 minus H3. But of course, don't forget that in our invention, the initial condition is that 60% of the total mass coming from input 1, that's your output at 3.3. So it follows that from mass balance, if this is 60%, this should be a 40%. Okay? And from thermodynamics 1, we know that H1 and minus H2, or the difference in enthalpy, could be expressed in terms of the specific heat at constant pressure, or that's a familiar formula, that is M, the mass multiplied by the specific heat multiplied by the change in temperature. You apply that also here on the other side, so that is Cp quantity multiplied by quantity T1 minus T3. T1 minus T2 is just simply 21 minus 79. Okay, so you have negative 58. The other one is T1 minus negative 18, so it gives you 39. If you consult your calculator, that is 0. So more or less the mass balances out and the energy balances out to 0. Okay, so the first law of thermodynamics is satisfied. The mass and energy balances, we have checked that, and that's okay. Now how about for the second law of thermodynamics? Is it followed? Let's try to see. Well, as a review, the change in entropy from 1 to 2 is given in terms of heat divided by the temperature. Of course, you need to add the entropy production inside the system. As you can recall, that's from our molecular dynamics simulation. Okay. So let's just try to write it in a more useful form. Okay. So this one could be expressed as in calculus form, this ds of the control volume. We need to add all of this heat divided by T. Okay, this is what you call the rates of entropy transfer, specifically by heat. This one is the entropy at the inlet, and this one is the entropy at the outlet. Of course, you need to sum all of it. Okay, we need to add the rate of entropy production, so that is sigma. Okay, so this is a more useful form for our design because it has an inlet and it has an outlet or exit. Okay, so we try to use this. Okay, since there is no heat transfer occurring in the system, might as well set that to 0, this one. So with some algebra, we're left with this. Okay, so we combine now the mass and entropy balances. Okay, from our mass balance, M1 is equivalent to M2 plus M3 again. M1 could be replaced by this, M2 plus M3, so multiplied by S1 minus M2 S2 minus M3 S3 for our exits, plus the entropy production, the control volume. By the way, the control volume is the imaginary, this is the enclosed by the imaginary line here. Okay, that's the enclosed volume. Now, of course, we can do a little bit of algebra to segregate M2 and M3. So that is S1 minus S2. This one is multiplied to quantity S1 minus S3. And if we recall from our previous from the previous assumption that 60% of what's coming out from M3 is from M1, the other one should be around 40%. Okay, plus the rate of entropy production. How do we evaluate this differences in entropy from S1 and S2 and S1 and S3? Well, okay, we can consult our previous formulation. If we try to remember that enthalpy minus temperature multiplied by entropy should be less than or equal to 0. Okay. Well, if we assume that this is the limit, so that should be a reversible process at constant pressure. Okay, so this one is an equality, so we drop the inequality here to simplify things. We assume that this is a reversible process, so by some algebra, that's TdS equals dH. Well, what is change in enthalpy from Thermodynamics 1? Enthalpy is internal energy plus PV, or pressure times volume. Well, if we consult our calculus, this is a product rule, so that is PdV plus VdP. Okay, well, if we assume that the pressure is constant, dV is 0, this one is reduced to du plus PV. Okay, that is your dH term, which is equivalent to TdS. Okay, so again, that's a very powerful equation. Okay, now how about for this equation below? Okay, you might notice that if we transfer this VdP in the other side, that's dH minus VdP, what's left is that we have du plus PdV, which is exactly this, our TdS. So your TdS might be written as dH minus PdV. Okay. Again, this one is a very powerful equation. TdS equals dH minus VdP. It came from this. Okay. Our initial argument that H minus T delta S is less than equivalent to 0. Okay. So let's move on. TdS equals dH minus VdP. Well, I have done this in the right side. TdS equals dH minus VdP. I have done the other one in the left side. Let's try to follow this one. TdS equals dH minus VdP. We divide it by T. By ordinary algebra, we get this expression. But remember that this enthalpy could be expressed in specific times temperature, or more specifically Cp dt. Okay. How about this V over T? Well, if we use ideal gas equation, that is just R over P. And if we try to integrate everything, we know that that's the natural logarithm ln T2 over T1. This is also integrated to natural logarithm P2 over P1. Okay, so again, that is the equation to evaluate difference in entropy from 1 to 2. Okay, so we use that. Okay, so in order for you to evaluate S1 minus S2, all you need to do is to use our equation, that is Cp ln of T2 over T1 minus R ln of P2 over P1. Okay, we apply the same formula here. This S1 minus S3, so we replace it by T3 and P3. Okay, now that's it. So that's a very compact formulation. We just have to input the values of the Cp. Remember that's 1. Then our pressures. Okay, that's 1 over 5. Our pressure here is 1 over 5 also. So our temperature in absolute scale is 352 over 294. The other one is 255 over 294. And if we consult our calculator by pressing everything, it turns out that this entropy production is positive. So what is your conclusion? Well, we have satisfied the first law of thermodynamics, that the mass and the energy balances out for the inlet and the outlet. It happens that within the control volume, the entropy production there is also positive. So we can say that on the basis of our evaluation, this invention is will not violate any principle of thermodynamics. Therefore, this is functional. This will work, and it's a very good design. Well, that's the application of the second law of thermodynamics, and I hope that you have learned how to utilize the second law of thermodynamics in order to evaluate if a certain invention will function. Okay, that's the claim. If the design is if the design will work, so we need to consult the second law of thermodynamics